Hello, everybody. Today we're going to dive into partial fractions a little bit more. So we're going to continue with where we left off yesterday. Yesterday we just kind of introduced the idea of partial fraction decomposition and how to do it. Today we're going to kind of build up into some slightly more difficult partial fraction decomposition problems. So here, let me share my screen and then we'll kind of dive into this. So to start, let's just recap kind of what we talked about yesterday. Basically, there are certain rational functions where they're just too hard to integrate. So what you need to do is you need to use an algebra technique to actually break them apart into simpler fractions. And the way you do that is essentially with these rules. So these are the rules that we're going to use, the same rules. But what we did yesterday, we didn't really have to use rule 0 and we didn't really have to use rule 3. Today I want to show you some examples where we would have to use those. So let's actually dive into this again. The thing that's different about this problem that we're going to start with today, I'll do another one in a second as well, or afterwards, but we're going to start with, let's say, all right, let me write this down. So let's take the integral of 3x squared. So 3x squared plus 1 over basically x plus 1 times x plus or x minus 5, let's say, squared. And then immediately, one thing you'll probably notice is that we have a repeated root now. And they've kind of already factored it for us. It would have been a lot more annoying if we had to factor it ourselves. So they've kind of done step 1 for us, actually. But here, this is where we have a repeated root, which we did not have last time. So we'll talk about how to handle that. So remember, step 1, we don't really care about the integral here. The real difficulty is actually just separate, like basically doing the decomposition. So let's take a look at this. So for step 0, what's the degree of the numerator? Hopefully it's clear that it's 2, right? Because that number, x squared. What's the degree of the denominator? That's a trickier question. The way to think about it is, hopefully it's clear that if you square this, it would be like x squared minus something plus something. You don't actually have to go through and do it. Just notice the highest term there is x squared. And then if you had like x squared plus dot 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 times x plus 1, well, think about what would happen then. We would basically be multiplying, you'd be multiplying x with all the terms over here. But the only one that really matters is the highest degree term. Because remember, we're just trying to find what the highest degree is. That's the degree of the polynomial in the denominator. Here, hopefully it's clear that x squared is the highest degree term. So x times x squared would be x cubed. In other words, even though it's in factored form, it's not actually expanded out into the form x cubed plus blah, blah, blah. We know that it would be if we actually multiply things out. So the degree of the numerator is less than the degree of the denominator. So for this problem, we're actually fine. We're good. So we don't need to do step 0 for this one either. And honestly, we don't need to do step 1 because it's already been done for us. They've already factored the denominator for us. It would have been a lot more annoying, like I said, if we start off with something, I'm just making this up, but if we start off like with something like this and we had to factor it, that would have been a lot more work. It would have been a lot more annoying. But we don't have to do that. So now the factors in the denominator on the left become the denominators in the terms on the right. So again, x plus 1 is a factor, so x plus 1 will be a denominator here, right? Plus x minus 5 is a factor, so x minus 5 will be a denominator here on the right. So hopefully that makes sense. That's step 2. And now step 3 is make sure that repeated roots on the left have multiple denominators on the right, counting up from 1 to the power. When I say the power, by the way, I mean whatever the root is. So here in this one, I should actually have another root, which is x, or another denominator, which is x minus 5 squared. Right? So you always start at 1 and then you count up to whatever this is. You might think you don't need this one. You might think, if you're not paying attention to step 3, that you just need to do x plus 1 is one denominator, x minus 5 squared is another. Actually not. I won't get into the mechanics of why that's required. It's kind of complicated. We can go into it maybe in another video. If you have any questions, just drop comments below and I can always create video, like basically whatever you want me to create a video on, I can prioritize that next time. But here, because that's a 2, you need to start from 1 and then count up to 2. If it was 3, this was like a 3, we would need to do another one where it's plus something over x minus 5 cubed. So hopefully that makes sense. So we actually do step 3 here. So we do step 3 here. And now step 4 is the numerators of each term on the right is a polynomial of degree 1 less than the denominator. So basically, the first two I think are pretty clear, right? So like this is, we talked about this yesterday. This is a first degree polynomial, so we need a 0th degree polynomial, which is just a number. And we just, because we need a lot of numbers sometimes, we just start at the beginning of the alphabet, and that way we have plenty of numbers. So this would be A, that would be B. You can't name them the same because you can't assume that they would be the same number. You need to choose different variables for that. And then here, this is where you might be tempted to say CX plus D. That's wrong, even though technically, if you look at the whole thing here, it is squared, like it is a quadratic. So you might think you need a first degree polynomial, but you kind of ignore, on the right at least, you ignore what's on the outside. You only care about the thing on the inside. So it's actually just going to be C, not CX plus D. And that's an important detail. So there you go. Hopefully that makes sense. Now, that's really all there is to it. So now we just need to combine these. And you'll see that because it's a repeated root that we're dealing with now, it's going to be a little bit harder to find A, B, C, and D. So we still need to do the same thing we did last time. At this point, we need to find, like, we have the setup correct, but now we need to find a common denominator. What is that? The thing on the left, by the way, this is always the common denominator. So we already know that's going to be a common denominator. I'm going to kind of jump to it. Like I won't go through every step. I assume you kind of understand how to do this part. But basically, I guess what I'm saying is what's preventing this from being that? The x minus 5 squared. So if you just multiply by x minus 5 squared, if you do it in the denominator, you also have to do it in the numerator. So that's why I'm going to write here a times x minus 5 squared. That's why I do that, because that's the thing preventing it from being the common denominator. And then here, what's preventing this thing? Another x minus 5 and another x plus 1. So that's why, and I have to do this again. If I multiply by that in the denominator, I also have to in the numerator. So it's going to turn out to be plus b times x minus 5 times x plus 1. And then for c, what's preventing that is really just multiplying by an x plus 1. So it'll be plus c times x plus 1. And we get that. Now, again, same story as before. This thing has got to equal that thing. We need to choose A, B, and C to make these equal for all possible values of A, B, and C. Or for all possible values of x, I should say. So here, I'm just going to copy this down. So we're going to get, we're going to get this. So we're going to get this. Let me copy this down. So going to have this. And then it's a little bit trickier now, right? The last time we just had 2 values. Because it's a repeated root now, we have 3. And also the part that this is a mixed one, you'll see why that's a problem in a second. But we're going to do the same strategy as before, but we're going to run into new problems that we didn't run into last time. So just fair warning on that. But basically, how do we do this? Think about it like this. Again, it's the same. You always want to start with the quick method. What you could do is turn this thing into a 3x3 system of equations. That's kind of annoying. You really don't want to do that, but you could. That is an option. You want to do the quick way first. What's the quick way? Remember, intelligently choose x, because this has to be true for any value of x, like this equation. So intelligently choose x values that will cause certain things to cancel out. That's the most clever thing you can do. So here, think about this. What would cause everything except A to get canceled out in this format? If you think about it, another way of asking that question is, what does every other term have as a factor that A does not? And the answer is x plus 1. That's the one that B and C have in common that A does not have in common. So if I choose an x value that would make that 0, like -1, for example, that would cleverly cancel out B and C. So if I do that, let's see what happens. I get 3 times -1 squared plus 1 equals A times -1 minus 5 squared plus B times, you can run through this if you want, -1 minus 5 times -1 plus 1 plus C times -1 plus 1. And then what do we get? We get a 4, right? And then we get, that'll be -6 squared positive 36, so 36A. And hopefully it's clear. That's 0, and that's 0. That was the whole reason we chose that x value. So when you solve this, what did we just learn? We learned that A is equal to 4 over 36. If we simplify that, I think that'll be 1 over 9. So there you go. Hopefully that makes sense. Now, looking at these, we can basically do the same strategy. Now, looking at B, B is actually kind of a problem here, right? What X value could we choose that makes B the only thing that doesn't go away? It's actually kind of a trick question, right? Because if we try to make A go away, we need to use 5 to make A go away. If we but that would also make B go away. That's the problem, because that has X minus 5 as a factor as well. If we want to make C go away, we would also have to use -1. But the problem is that would also make B go away. So like no matter which one we choose, B is going to disappear. We're not going to be left with just B. That's kind of a problem, which means we're not going to be able to solve for B by doing it that way. So I'm actually going to hold off on B. That's a little bit trickier. Let's actually find C. That one we can actually deal with. So ask yourself the question: what does C, or basically what do A and B have in common? Those terms, in terms of factors, that C does not. And hopefully it's clear. The answer is X minus 5. So if we just cleverly make that 0 by plugging in X equals 5, what will happen? We'll get 3 times 5 squared plus 1 equals, and I won't write it all out this time, but we'll get 0 because that's going to cancel out, right? We'll get 0 because that's going to cancel out. So 0 plus 0, and then plus C times 5 plus 1. So in other words, what is this going to be? This is going to be 25. So 5 squared, 25 times 3, 75. Plus 1, 76 equals 6 times C. And then you can say C is obviously 76 over 6. What is that? I don't know, but they're both divisible by 2. So if we just cut them both in half, 70 divided by 2 is 35, and then 6 divided by 2 is 38, or sorry, 3. So add those together to get 38. 38 thirds. Can you simplify further than that? I don't think so. If it's 39 thirds, that would be 13, but this does not factor cleanly. So I'll just say that's basically the best we can do, it looks like, in terms of an improper fraction. So so C is 38 over 3. So at least we found A and C. We haven't found B yet. That's a bit of a problem, as we said, but we at least found A and C. Now, how do we find B? Remember, we can't really use that clever trick anymore, or at least we can't in its current format. Like here, think about it like this. We now, the trade-off is we now know A and C at least. So you can kind of get rid of those, right? So if I plug in A equals 1/9, right, plus B times X minus 5 times X plus 1 plus 38 over 3 times X plus 1. So if we list these out, we at least get, like we've at least solved A and C. We just haven't solved B yet, so we still need to do that. But the way we can do this, it's a kind of a clever trick. We're actually not going to do the thing that we did before. Remember, before we were cleverly choosing points that make essentially everything except the thing we want cancel out. We already talked about how that's not really possible now with B, right? But what you can do is you could just plug in whatever value you want, and that would actually work here. So here, once you solve for A and C, you can just plug in any X value, and then you'll be able to solve for B, right? Because you have one equation, one unknown after you plug in some X value. So basically just ask yourself, what's the easiest X value that you could plug in that doesn't cause these to cancel out? So you can't do 5, you can't do 1, right? Because that'll cause B to disappear as well. We need B to stay so we can solve it. I would just choose 0. So for this one, again, maybe in different cases it would be different, but when you do that, you get 0 plus 1 is 1, and then we get 0 minus 5 is -5 squared, 25 over 9, 25 ninths, plus -5 times 1, so I'll say minus 5b, plus 38 over 3. That's what I would say. There you go. Hopefully that makes sense. And now if you wanted to find a common denominator, at least with these two, right? If you want to get those as a common denominator, I would make 9 the common denominator, right? So this will be 9, multiply the denominator by 3 to get 9, multiply the numerator by 3 to get what? Well, 40 would be 3 times 40 would be 120. So look at 38 as 40 minus 2 times 3. And then that would be 120 minus 6. That would be 114, I think, right? So 114. And then if we add those together, 114 plus 25, 139. So basically you get, and then subtract that to the other side, 1 minus 139 divided by 9. And if you want to get common denominators here, you could say 9 and 9. 1 is 9/9. So it seems like negative 130 over 9 equals -5b. divide by -5 now, that would just be 26/9. So hopefully that logic is clear that we get 26/9 when we work that through. And by the way, here's another tiny little mental math trick when you're doing this. When you're doing, like, let's say 130 divided by 5, you could actually do that. Or what you could do, there's a clever trick. What if you just did times 2 divided by 10? 2/10 is 1/5. So dividing by 5 is the same as just, like, I guess my point is the quicker way to do it is just double and cut off a 0. That's what I did. So, like, 260, that's easy, and then cut off a 0, 26. That's the fast way to do it. Again, it's a little mental math trick. You don't really need it, but just pointing that out. So long story short, we are able to solve for p. Again, the way we did it is weird compared to what we did last time. We basically plugged in some random value that didn't cause things to cancel out, and there we were able to solve for p. So to put all this together, let me remember, this was our original setup. And what did we figure out throughout this process? We figured out that A was equal to 1/9, right? We figured out that B was equal to 26/9. And then we figured out that C was equal to 38 thirds, or 114/9, whatever you want to say. So there you go. We've successfully found the partial fraction decomposition. And now let's check this, by the way. So if I go to Desmos, and if I actually try to check this thing, so we have 3x squared. So we have 3x squared plus 1 all over x plus 1 times x minus 5 squared. So this is the weird function we're dealing with here. X plus 1 times x minus 5 squared. And then on the right, what do we have? We have 1/9 divided by x plus 1. Or was that x minus 5? Yeah, or no, x plus 1. And then we have plus 26/9 over x minus 5 times x plus 1. And then plus 38 thirds. And actually, it's probably easier just to write A, B, and C, and then I'll play with them afterwards. So A, B, and C, so divided by x minus 5 squared. So for all these A, B, and C values, you can kind of play around with them. So like it seems like A's got to be something like that. B, what are we going to do with B? What are we going to do? Okay, so maybe stretch that out. And you can kind of mess around with these more or less. And then, yeah, so maybe we just got to increase that. So 13, or let's say 13, something like that. And you can kind of mess around with these values until you get something that works. So it's like, but we already kind of know what works, right? We said A is going to be 1/9. B is going to be 26 over 9. And then C is going to be 38 over 3. Is that what we said? 38. Did I write that correctly? Oh, sorry. There you go. That fixes it. So yeah. So x plus 1, denominator is x plus 1, x minus 5, x minus 5 squared. And there you go. These numbers now work. So here, yeah, you can see that it's right on top of the actual function. So there you go. This is the correct partial fraction decomposition. Now, if you just want to integrate that, it's actually not that hard, right? So the hard part is the algebra actually for these, like the actual partial fraction decomposition. Sometimes, to be clear, sometimes the integral is hard. Here, it's actually not. So here, this one's easy. I won't go through all of it, but this, we talked about that yesterday, the 1/9 natural log x plus 1, basically. Same thing here, just with slight difference. This one's a little different. Think of it like, basically, I'll just give a hint. Do a u sub with u equals x minus 5. Set u equal to the inner function, which in this case is clearly that. Factor out the 38 over third, and then it's not that bad. So there you go. That's how you would do this. That's how you would do this partial fraction decomposition with a repeated root. If you have any questions on that, like I said, feel free to just drop it below in the chat. Otherwise, what we'll do is we'll kind of go through and we'll kind of introduce an additional one, let's say. So, or actually, I think I'll hold that off until tomorrow, unless anybody has like any burning questions. Like I said, feel free to drop them in the chat or just post them in the Skool community. And then what we'll do, because it's gonna take us a while, I'm noticing, to get into that. So we'll get into it tomorrow probably. Feel free to, like I said, just drop any questions. Otherwise, I will catch you guys tomorrow, and we'll continue with these. and we'll talk about kind of more advanced partial fraction decomposition because it does get pretty advanced. So hope that helps and hope that makes sense for today. And I will see you guys tomorrow. Bye.